For hundreds of millions of years, Earth's climate has swung between warm oceans and advancing ice. But in the Cryogenian Period around 720 to 635 million years ago, something far more extreme unfolded. Glaciers may have reached almost to the equator, continents lay buried under ice, and the planet edged close to becoming a true Snowball Earth. Today we explore these cryogenian glaciations and what they reveal about how a world can freeze, survive, and eventually thaw. If you enjoy calm journeys into deep time, please like, subscribe, and share, and tell us in the comments what would you ask about living through Earth's most extreme ice ages. Thank you for watching. Now let's begin. In the late Proterozoic Earth orbits a sun that is slightly fainter than the modern star, yet the planet still maintains widespread oceans and an active hydrological cycle. Stellar evolution models indicate that the young sun emits less radiant energy than it does today, so the amount of solar power reaching the top of Earth's atmosphere is reduced compared with the present. Geological evidence, however, shows long intervals with liquid water and moderate climates rather than a permanently frozen world. The apparent mismatch between weaker solar input and a mostly temperate early Earth is often called the faint young sun problem. Climate models and geochemical studies suggest that one way to offset the reduced solar energy is to maintain higher concentrations of greenhouse gases than those of the modern atmosphere, while another is to alter cloud cover or surface reflectivity in ways that allow more energy to be retained. In practice, the solution probably involves a combination of these factors, with greenhouse gases playing a major role over long time scales. To keep surface temperatures above the freezing point of seawater over geological time, the planet depends on a combination of greenhouse gases, cloud behavior, and surface reflectivity that together regulate how much incoming energy is absorbed and how much is lost back to space. Carbon dioxide, methane, and water vapor in the atmosphere absorb outgoing infrared radiation, while clouds and bright surfaces such as ice and snow reflect a fraction of incoming sunlight. This balance between incoming solar radiation and outgoing long-wave radiation forms the physical backdrop for every later climate state, including the extreme ice ages of the Cryogenian. In this context, long-term climate is shaped by slow shifts in solar luminosity, atmospheric composition, and the evolving layout of continents and oceans rather than by rapid external forcing. The Proterozoic eon spans roughly from 2.5 billion years ago to a little more than 540 million years ago, bridging the gap between the older Archean world and the more familiar Phanerozoic interval with abundant animal fossils. During most of this long eon, Earth's crust stabilizes, large continents assemble and break apart, and the atmosphere and oceans undergo major chemical changes. Early in the Proterozoic, atmospheric oxygen is still low, following the first great rise during the earlier Great Oxidation event. Over hundreds of millions of years, oxygen continues to accumulate in steppes affected by volcanic gas release, burial of organic carbon, and weathering of rocks on land. By the Neoproterozoic era, which occupies the final part of the Proterozoic, oxygen levels in the atmosphere and surface ocean are higher than before, but still do not match modern values, and deeper waters can remain poorly ventilated and low in oxygen. Many studies group these later increases into a Neoproterozoic oxygenation event, a prolonged interval during which the deep ocean becomes more oxidized, and conditions slowly approach those that later support diverse animal life. Carbon dioxide and other greenhouse gases are also controlled by long-term feedbacks between volcanoes weathering and sediment burial. Together, these slow processes form an Earth system that is sensitive to tectonic and geochemical disturbances and capable of large climate responses. Climate records from rock suggest that the Proterozoic climate is not uniform. In the early part of the eon, there are prolonged intervals of relatively stable conditions, sometimes referred to as the boring billion, with fewer large swings in climate and in the chemistry of seawater. Even during these quieter times, Earth experiences smaller glaciations, and evidence from sedimentary rocks indicates that glaciers reach low latitudes more than once in the distant past. The planet's position in the solar system remains fixed, so changes in climate arise from internal factors such as continental configurations that alter ocean currents and atmospheric circulation, or variations in greenhouse gas concentrations that shift the global energy balance. As continents merge into and rift away from supercontinents, they influence how heat and moisture are redistributed over the globe, and they change where chemical weathering is most active. Weathering rates in turn control how quickly carbon dioxide is removed from the atmosphere and locked into carbonate rocks and other minerals. By the time the Neoproterozoic begins around 1 billion years ago, this coupled system of tectonics, geochemistry and climate has been operating for a very long time. Continents are again assembled into large land masses, and ocean basins and continental margins are rearranged. At the same time, the sun is still modestly fainter than today, so climate stability depends strongly on maintaining sufficient greenhouse gas levels. Geochemical proxies from ancient rocks, including carbon and sulfur isotopes, point to changes in the cycling of carbon and oxygen through the oceans and atmosphere during this era. These changes affect both the greenhouse properties of the atmosphere and the redox state of the oceans, with consequences for the distribution of early complex life. The Neoproterozoic also sees further steps in oxygenation, although estimates of exact concentrations and timing differ between studies. What is clear is that the climate system is capable of large responses when boundary conditions shift, for example, when volcanic outgassing, continental breakup or biological innovations alter the long-term balance between sources and sinks of greenhouse gases. Within this broader Proterozoic and Neoproterozoic context, the Cryogenian period occupies a distinctive interval in which Earth's climate departs from the more moderate states that precede and follow it. The Sun is still slightly less luminous than at present. Continental positions differ markedly from modern configurations, and atmospheric composition continues to evolve. Geological evidence from cryogenian-aged rocks shows that during this period glaciers advance to unusually low paleolatitudes, and the ice-related deposits occur on many continents. These records indicate that the climate system, already shaped by a faint yet slowly brightening sun, and by progressive oxygenation and carbon cycle change, can enter regimes much colder than most of Earth's history, and that the Cryogenian period marks one of the most extreme cold states reached under these boundary conditions. Long before the Cryogenian ice ages begin, Earth's climate system has already passed through several distinct modes, and has demonstrated that it can support both very cold and relatively stable temperate states over hundreds of millions of years. Sedimentary rocks from the Paleoproterozoic more than 2 billion years ago record several large glaciations grouped within what is now called the Huronian supergroup in Canada, with additional evidence from South Africa and other regions. In these successions, layers of poorly sorted glacial sediment known as diamictites overlie and underlie non-glacial strata, implying repeated advances and retreats of continental ice. Paleomagnetic measurements on some of these formations suggest that at least part of the glacial material is deposited at low paleolatitudes, rather than near the poles, raising the possibility that ice sheets extend into the tropics during some portions of these early ice ages. A younger Paleoproterozoic unit, the Macanian Formation of southern Africa, also appears to be laid down close to the paleoequator, and contains features that many researchers interpret as glacial in origin. These observations have inspired the idea that Earth may have entered one or more snowball-like states during the Paleoproterozoic, when the planet's oceans and continents are heavily ice-covered for extended intervals, and open water is greatly restricted. Although there is still debate over the exact extent and duration of these early ice ages, the rocks demonstrate that the climate system is capable of sustaining widespread glaciation when boundary conditions allow greenhouse forcing to fall and surface reflectivity to rise. One proposed trigger for these Paleoproterozoic glaciations links them to the first large rise of atmospheric oxygen, the Great Oxygenation Event. Before oxygen becomes abundant, methane produced by microbial activity may serve as an important greenhouse gas, helping to maintain liquid water under a faint sun. As oxygen levels rise, methane is oxidized and removed from the atmosphere, reducing its greenhouse effect. With less methane and limited compensating increases in carbon dioxide, global mean temperature can fall to the point where continental ice sheets expand and sea ice spreads over large areas of ocean. Climate model studies show that once ice sheets grow to sufficiently low latitudes, the reflective surface of snow and ice causes additional cooling by sending more incoming solar radiation back to space, making it easier for glaciation to persist. The Paleoproterozoic record therefore provides an early example of how biological and geochemical change can alter atmospheric composition and push climate into a very cold regime. At the same time, geochronological and stratigraphic evidence indicates that even these severe ice ages do not freeze the planet permanently. Intervals of glaciation are separated by non-glacial periods, and eventually the balance between volcanic outgassing of carbon dioxide and its removal by weathering shifts, allowing greenhouse gas concentrations to rise again and ice to retreat. After these Paleoproterozoic glaciations end, the geological record moves into a long interval with far fewer signs of large-scale climate swings. The stretch from roughly 1,800,000,000 to about 800 million years ago is often described as the boring billion, an informal term that refers to apparently muted variation in climate and ocean chemistry, compared with the more dynamic intervals before and after. During much of this time, there is little clear evidence for prolonged continental-scale glaciation, and many sedimentary successions suggest relatively stable temperate surface conditions. Marine geochemistry and fossil microfossil assemblages imply that oxygen levels in the atmosphere and surface ocean stay modest, while deeper marine waters often remain poorly ventilated and can be low in oxygen or chemically stratified. This combination of moderate climate-limited oxygenation and relatively slow biological innovation gives the impression of an Earth system that is slowly evolving but not undergoing abrupt climate transitions. Recent work, however, shows that this interval is not truly static. Reconstructions of plate motions and numerical models of deep-time carbon cycling indicate that the breakup and assembly of supercontinents during the boring billion influences the distribution of shallow sea subduction zones and volcanic arcs. Expanded regions of shallow continental shelf can host productive marine ecosystems that draw down carbon and affect redox conditions, while changes in the length and activity of subduction zones alter the long-term rate of volcanic outgassing. Even so, the climate response inferred from the available stratigraphic and geochemical data remains relatively muted, suggesting that feedbacks between weathering carbon burial and outgassing keep global temperatures within a comparatively narrow range for many tens of millions of years. In this sense, the mid-Proterozoic climate can be viewed as a long test of the stability of Earth's regulatory mechanisms under modest solar input and slowly changing atmospheric composition. As the Neo-Proterozoic approaches, the climate record shifts again, The Tonian period immediately preceding the Cryogenian contains stratigraphic units in several regions that have been interpreted as glacial in origin, though their exact ages and global significance are still under investigation. Some of these deposits historically associated with events named Kygus, or early Neoproterozoic glaciations, may record more limited regional episodes of ice expansion rather than planet-wide snowball states, and some may ultimately prove to be time equivalents or precursors of later Cryogenian glaciations once dating is refined. Regardless of their precise classification, these Tonian units are important because they mark the apparent return of glaciation after a long interval with little evidence for large ice sheets. Combined with changing carbon isotope patterns in marine carbonates and indications of evolving ocean redox structure, they point to an Earth system that is leaving behind the relative climatic stasis of the mid-Proterozoic and becoming more responsive to tectonic and geochemical perturbations. By the time the Cryogenian period begins, Earth has already experienced at least one earlier era of possible low-latitude glaciation and a prolonged stretch of comparatively steady climate. The long climate arcs leading into the Cryogenian therefore include both earlier experiments in extreme cold and a billion-year demonstration of climate regulation, providing the broader temporal setting in which later more severe ice ages take shape. In the later Tonian and earliest Cryogenian, Earth's climate begins to move away from the comparatively stable state that characterizes much of the mid-Proterozoic and toward a regime in which large disturbances in the carbon cycle and tectonic configuration have stronger climatic consequences. Continents are assembled mainly within the supercontinent Rodinia, which brings large areas of land into low and middle paleolatitudes and leaves other regions occupied by wide ocean basins. This arrangement affects how heat is distributed between equator and poles and how moisture circulates through the atmosphere, because land and sea respond differently to incoming solar radiation and to changes in greenhouse gas concentrations. When broad tropical land masses are exposed, warm and wet conditions favor chemical weathering of silicate rocks, a process that consumes carbon dioxide as it converts fresh minerals into clays and dissolved ions that are eventually carried to the ocean. Over long periods, this chemical uptake of carbon dioxide acts as a negative feedback on climate cooling the surface when temperatures rise. In the late Tonian to early Cryogenian, however, several lines of evidence indicate that this feedback may become strong enough or fast enough to draw down greenhouse gas levels to unusually low values. As rifting begins to disrupt Rodinia, newly uplifted rift flanks and volcanic provinces expose fresh basaltic rock to weathering. Large igneous provinces, such as those emplaced in high-latitude regions of the Northern Hemisphere, produce vast areas of young chemically reactive rock that are particularly efficient at removing carbon dioxide from the atmosphere when climates are warm and precipitation is abundant. Radioisotopic dating places at least one of these volcanic episodes only a short interval before the first well-constrained Cryogenian glaciation, which suggests that volcanism and subsequent weathering are closely linked in time with the transition into an icehouse state. At the same time, changing seafloor spreading rates and the structure of mid-ocean ridges influence how much carbon dioxide is released from the mantle through volcanic degassing. If outgassing remains steady or declines, while weathering intensifies, the long-term balance between sources and sinks of carbon dioxide shifts toward net removal and global mean temperature falls. Carbon isotope records from marine carbonate rocks of this age show large excursions away from typical Proterozoic values, which researchers interpret as signs of major reorganization in the global carbon cycle. In some successions, negative carbon isotope shifts imply intervals when a large fraction of organic carbon that would normally be buried and preserved is instead oxidized and return to the ocean atmosphere system. In others, patterns in the isotope data suggest changes in the partitioning of carbon between surface reservoirs and deeper parts of the ocean. One prominent negative excursion identified in carbonate units that crop out today in North Atlantic regions illustrates how widespread and coherent these anomalies can be. Similar disturbances in carbon isotope ratios are recognized on other ancient continental blocks, which supports the view that the signal reflects global scale adjustments rather than isolated local events. Although the detailed causes of each excursion remain under active study, the combined signal demonstrates that the carbon cycle is not in a steady state, and that reservoirs of carbon are being redistributed in ways that are compatible with a gradual decline in greenhouse gas forcing over millions of years. At the same time, stratigraphic and sedimentological evidence records a renewed appearance of glacial deposits that differ from those of the much older Paleoproterozoic examples and from the nearly non-glacial record of the mid-Proterozoic. In several regions, including what are now North America, Australia, and other fragments of ancient continents, late Tonian to early Cryogenian sedimentary successions contain diamictites, dropstones, and striated clasts that are most simply explained by the presence of land-based ice flowing into marine or lacustrine basins. Paleomagnetic measurements on some of these units indicate deposition at relatively low paleolatitudes, implying that glaciers advance well away from polar regions. Certain formations once assigned to separate earlier Neoproterozoic glaciations have been reinterpreted with improved dating and correlation, so that many workers now regard the first unambiguous Neoproterozoic ice age as coinciding with the onset of the Cryogenian, rather than as a distinct older event. This refinement underscores that the approach to the Cryogenian does not consist of numerous short isolated glaciations, but instead reflects a gradual transition from long-term climatic stability to conditions that allow large, long-lived ice sheets to form when thresholds are crossed. In parallel, reconstructions of plate motions and volcanic histories suggest that the emplacement and subsequent weathering of large igneous provinces in the high latitudes of one hemisphere occur only a short time before the first major Cryogenian glaciation. When these basaltic provinces cool and interact with the atmosphere and hydrosphere, they provide expanded surfaces for rapid chemical weathering, especially under warm, wet conditions that may still prevail at low latitudes just before widespread glaciation. Changes in ocean circulation that accompany the progressive breakup of rodinia further influence how heat and dissolved substances move between equatorial and polar regions, and they modify the delivery of nutrients to the surface ocean. These effects can alter biological productivity rates of organic carbon burial, and the redox structure of the ocean adding additional pathways for the carbon cycle to shift away from its previous balance. In addition, the slow but steady brightening of the sun continues, and yet the emerging pattern of lower greenhouse gas concentrations and more reflective surfaces means that this additional solar energy does not translate into sustained warming. The combined influence of tectonics, volcanism, weathering, evolving ocean circulation, and solar input is to lower greenhouse gas concentrations, adjust ocean chemistry, and bring global mean temperatures closer to the point at which ice can expand from high latitudes into the subtropics. In this evolving setting, Earth enters the early Cryogenian with a climate system that is increasingly sensitive to modest additional perturbations in the carbon cycle, continental configuration, or solar input, and only a small further change is needed for ice sheets to begin their advance into regions that have been ice-free for much of the preceding Proterozoic. At the opening of the Cryogenian period, Earth's solid surface is dominated by the supercontinent Rodinia, whose fragments are distributed in a pattern very different from that of today's continents. reconstructions based on paleomagnetic measurements, structural geology and correlations of rock units suggest that large continental blocks such as Laurentia Australia, Antarctica, and parts of what will later become Asia and South America are joined together or lie close to one another, many of them situated at low and middle paleolititudes. In some models, Laurentia occupies a near equatorial position, while other cratons are arranged around it in an approximately ring-like pattern. In alternative configurations, some blocks lie at somewhat higher latitudes, but most solutions agree that extensive land areas are located away from the poles. This placement matters because continents interact with climate differently from oceans. Land surfaces respond more quickly to changes in solar heating, develop stronger seasonal temperature contrasts, and host the majority of long-term silicate weathering that consumes carbon dioxide. When wide belts of land lie in the tropics where incoming solar radiation is greatest and rainfall can be abundant, the potential for chemical weathering to remove carbon dioxide from the atmosphere is high. If tectonic uplift exposes large areas of fresh rock in these latitudes, weathering can be especially efficient. As Rodinia begins to rift new passive margins and rift shoulders, form generating relief and exposing unweathered rocks to tropical climates. The breakup process also reorganizes the pattern of ocean basins and seaways. Narrow, newly opened oceans separate continental blocks that were previously contiguous, and long continental margins face these basins. The geometry of these margins influences how surface currents, deep water formation and upwelling cells develop. Through these effects on ocean circulation, plate motions help set regional patterns of sea surface temperature, sea ice distribution, and nutrient supply to surface waters. Within the interior of Rodinia, broad continental regions rise to moderate elevations and are drained by river systems that flow towards surrounding shallow seas. Weathering on these landmasses releases calcium, magnesium, and bicarbonate ions into rivers which transport them to the ocean, where they eventually form carbonate minerals. This flux of dissolved material represents a key pathway by which atmospheric carbon dioxide is converted into solid carbonate sediments and stored over geological periods. The rate of this process depends on temperature, precipitation, rock type, and the presence of soils and vegetation. During the cryogenian complex, land plants have not yet evolved, so soils are simpler than in later eras, but microbial and early eukaryotic communities can still influence weathering rates. Basaltic rocks created by earlier and ongoing large igneous province activity are particularly reactive under warm, wet conditions and can drive relatively rapid drawdown of carbon dioxide when exposed over large areas. At high latitudes, the positioning of some continental blocks allows ice sheets to grow when conditions cool, but the presence of substantial low-latitude land means that once ice extends equatorward, it can cover broad areas of continental crust, rather than being confined to polar regions. The distribution of continents also affects the thermal inertia of the surface. Large ocean basins at low latitudes can store and transport heat-moderating temperatures, whereas extensive low-latitude land tends to heat and cool more rapidly and can favour stronger seasonality. During intervals when greenhouse gas concentrations are reduced, this arrangement makes it easier for seasonal snow cover to persist on land from one year to the next and for small ice caps to expand. Numerical climate models that incorporate these reconstructions test how different Rodinia configurations respond to reduced carbon dioxide levels and varying solar input. Many such experiments show that for plausible cryogenian continental layouts, a decline in atmospheric carbon dioxide to values significantly below modern pre-industrial levels is sufficient to allow sea ice to grow equatorward, especially if the land distribution enhances weathering and if cloud and aerosol properties are favorable to cooling. Once sea ice begins to expand out of polar regions, its high reflectivity strengthens the cooling. At the same time, the seafloor beneath the oceans that surround and penetrate Rodinia participates in long-term geochemical cycles. Mid-ocean ridges, subduction zones and back-arc basins release volatiles including carbon dioxide from the mantle. Subduction of oceanic lithosphere carrying carbonate and organic carbon delivers previously stored carbon back into regions where it can be degassed. The total volcanic output depends on the length and activity of these tectonic features, which are set by the rate and geometry of plate motions. If Rodinia's configuration at the start of the Cryogenian corresponds to a stage with reduced ridge length, or modified subduction patterns, then the net outgassing of carbon dioxide could be lower than during earlier intervals even before enhanced weathering is considered. Combined with efficient weathering on newly uplifted rift shoulders and tropical continents, this imbalance between sources and sinks of carbon dioxide promotes cooling on multi-million-year timescales. Sedimentary basins along the margins of Rodinia record the response of the surface environment to these changes. Successions of shallow marine carbonates, clastic sediments, and volcanic clastic layers show variations in thickness faces and geochemical signatures that can be related to regional subsidence sea level change and evolving ocean chemistry. In some basins, thick carbonate platforms prograde into adjacent deeper water settings, indicating long periods of stable, relatively warm conditions prior to glaciation. These carbonate successions often terminate abruptly with the onset of diamictites and other glacially influenced deposits, marking a shift from carbonate-dominated deposition under open water conditions to mixed or clastic regimes shaped by ice sheets and ice rafts. The sharpness of this transition in the rock record is consistent with the idea that once certain thresholds in greenhouse gas, concentration and continental ice volume are passed, climate can shift from a state characterized by limited or no low-latitude ice to one in which glaciers can quickly expand. The configuration of Rodinia and its surrounding oceans at the beginning of the Cryogenian therefore provides the physical framework in which these shifts occur, setting the distribution of reactive rocks, the pattern of ocean basins, and the geometry of potential ice sheet growth without by itself dictating the exact timing or magnitude of the glaciations that will follow. Across the Cryogenian world, the long-term carbon cycle operates as a slow coupled system, connecting Earth's interior. Its surface rocks the oceans and the atmosphere. Carbon dioxide enters the atmosphere primarily through volcanic and metamorphic degassing at mid-ocean ridges, volcanic arcs, continental rift zones, and large igneous provinces. Magmas, rising from the mantle, release carbon dioxide that has been stored in deep reservoirs, and metamorphic reactions in crustal rocks liberate additional carbon when carbonates and organic rich sediments are heated and transformed at depth. Once in the atmosphere, carbon dioxide mixes with water vapor and participates in the greenhouse effect, absorbing outgoing infrared radiation and helping to maintain surface temperatures compatible with liquid water. At the same time, atmospheric carbon dioxide dissolves in rainwater to form weak carbonic acid, which reacts with exposed silicate minerals on continental surfaces. This process of silicate weathering breaks down feldspars, pyroxenes, and other rock-forming minerals into clays and dissolved ions. Rivers carry the resulting bicarbonate calcium and magnesium into the ocean, where they are eventually incorporated into carbonate minerals that settle to the seafloor and become part of sedimentary strata. Over millions of years, this sequence of degassing, weathering, transport, and burial establishes a feedback loop often called the carbonate-silicate cycle that links climate to tectonics. When climate is warm and rainfall is abundant, chemical weathering rates tend to increase, pulling more carbon dioxide out of the atmosphere and depositing more carbonate in marine sediments. When climate cools and weathering slows, volcanic and metamorphic degassing can outpace carbon removal, leading to gradual accumulation of atmospheric carbon dioxide. In this way, the carbon cycle tends to limit departures from moderate climate states over long intervals, although it can also amplify or sustain deviations when external or internal boundary conditions shift. During the cryogenian tectonic and magmatic conditions create circumstances in which this carbon cycle feedback becomes particularly effective at cooling the planet. The breakup of rodinia generates rift zones, new passive margins, and large igneous provinces that together expose vast areas of fresh mafic rock to weathering. Basalts and related rocks contain high proportions of minerals that react quickly with carbonic acid, especially in warm and wet tropical climates that characterize many low-latitude regions before full glaciation. As rifting uplifts crust along fault-bounded shoulders, these young rocks are elevated into climatic zones, with frequent rainfall and strong temperature contrasts, which further enhances chemical breakdown. Rivers draining these highlands deliver large fluxes of dissolved ions and silica to surrounding seas where carbonate precipitation and burial can increase. Because the rate of silicate weathering depends strongly on temperature and runoff, initial cooling that follows from moderate carbon dioxide drawdown does not immediately stop the process. If greenhouse gas concentrations fall, while low-latitude continents still support vigorous weathering, the carbon cycle can remain in a state where removal of atmospheric carbon dioxide continues at a pace that pushes climate toward progressively colder conditions. The ocean participates in this evolving balance through both inorganic and biological pathways. Inorganic carbonate precipitation on shallow platforms converts dissolved inorganic carbon into solid minerals, while organisms that produce carbonate skeletons and tests contribute to biogenic carbonate production where they are present. During the cryogenian complex, calcifying organisms are not yet widespread but microbial mats, and early eukaryotic communities can still influence local carbonate formation and organic carbon burial. When productivity in surface waters increases, more organic matter sinks into the deep ocean and is either oxidized or buried. Burial of organic carbon represents a net sink of carbon from the surface reservoir, because the corresponding carbon dioxide that was taken up during photosynthesis is not returned to the atmosphere and ocean through respiration. If burial rates rise, they can lower atmospheric carbon dioxide on long time scales, complementing the effects of silicate weathering. Redox conditions in the deep ocean modulate how much of this sinking organic matter is preserved. In low oxygen or stratified waters, a larger fraction of organic material can escape degradation and enter the sedimentary record. Geochemical traces from cryogenian and immediately pre-cryogenian rocks indicate that large parts of the deep ocean may be low in oxygen, or contain dissolved reduced species such as ferrous iron and sulfide conditions that can favor enhanced preservation of organic matter in some settings. Changes in nutrient delivery from continents driven by intensified weathering and shifting river systems modify marine productivity patterns and thus the efficiency of this biological carbon pump. Seafloor processes add further complexity. Hydrothermal circulation at mid-ocean ridges facilitates reactions between seawater and newly formed oceanic crust, a process known as seafloor weathering. These reactions consume carbon dioxide and alter the chemistry of both basalt and seawater, contributing an additional sink for carbon. The rate of seafloor weathering depends on ridge length spreading rate and hydrothermal flux, as well as on bottom water temperature, which itself responds to global climate. If spreading rates are high, The area of young reactive crust is large, and the potential for carbon dioxide uptake through these pathways increases. In the Cryogenian, the exact balance between seafloor weathering and ridge degassing remains uncertain, but both processes tie the state of the ocean floor to the evolution of atmospheric composition. When combined with continental weathering and organic carbon burial, they help determine whether total sinks outweigh sources over multi-million-year spans. Volcanic and metamorphic sources of carbon persist throughout the Cryogenian, even as surface conditions move toward extreme cold. Subduction zones beneath volcanic arcs release carbon dioxide derived from subducted sediments and altered oceanic crust. Continental collision zones and deeply buried basins experience metamorphism that liberates carbon from carbonate and organic-rich rocks. The magnitude of these fluxes varies as plate boundaries migrate, arcs grow or wane, and mountain belts rise and erode. If during key intervals leading into major Cryogenian glaciations degassing rates are modest, while weathering and burial remain strong, the net effect is an extended period of declining atmospheric carbon dioxide. Because the carbonate-silicate feedback operates on timescales of hundreds of thousands to millions of years, the approach to very low greenhouse gas levels is gradual, but once reached, these levels can be maintained until other factors intervene. Throughout this interval, the carbon cycle does not operate in isolation from other elements. Sulfur, phosphorus, and iron cycles all interact with carbon through their roles in nutrient limitation, redox reactions, and mineral precipitation. For example, enhanced weathering that delivers more phosphorus to the ocean can stimulate primary productivity, alter organic carbon burial, and influence oxygen levels in surface waters. Changes in sulfur cycling can shift the balance between sulfate reduction and other microbial pathways affecting both the isotopic composition of sulfur and the structure of redox gradients in the water column. These interactions are reflected in the combined isotope records of carbon-sulfur and other elements preserved in Cryogenian sedimentary successions. The presence of large coherent excursions in these records indicates that the coupled cycles experience significant reorganizations rather than minor local fluctuations. Within the Cryogenian, the slow adjustment of this network of processes produces an Earth system in which atmospheric carbon dioxide can reach much lower values than during most of the preceding Proterozoic. The long-term carbon cycle responding to tectonic uplift seafloor renewal, evolving ocean chemistry and biological activity, continues to operate as a regulator of climate, while also allowing the planet to approach conditions under which sustained low-latitude glaciation becomes physically possible. As Cryogenian conditions continue to evolve, the combination of low greenhouse gas concentrations, a faint sun, relative to the present, and the distribution of continents and oceans brings the climate system close to thresholds at which ice can expand rapidly from high latitudes toward the equator. Simple climate models that track the balance between incoming solar radiation and outgoing long-wave radiation often represent the surface as bands of latitude with an ice line that separates reflective ice-covered regions from darker ice-free areas. In these energy balance frameworks, the position of the ice line controls how much solar energy is absorbed, because ice and snow reflect a larger fraction of sunlight than open ocean or bare rock. When greenhouse gas concentrations are high and solar input is sufficient, the stable solutions place the ice line at relatively high latitudes, with ice confined near the poles, and lower latitudes remaining ice-free. As greenhouse forcing weakens or solar input decreases, the models show the ice line moving equatorward, increasing the area covered by bright ice and reducing the amount of energy the planet absorbs. This sets up a positive feedback often called the ice albedo feedback, in which expanding ice causes further cooling, which in turn allows ice to spread still farther. At a critical point, the models exhibit an instability once the ice line reaches roughly 30 degrees latitude in either hemisphere. A small additional cooling can cause the climate to jump from a partly glaciated state to one in which ice extends to very low latitudes or fully encircles the globe. In this globally glaciated solution, sea ice and snow cover much of the planet's surface, and the average reflectivity is so high that even with continued solar input, surface temperatures remain far below the freezing point of seawater. The exact latitude and forcing at which this instability occurs depend on model details, including how clouds, water, vapor, and atmospheric heat transport are represented. But the general behavior of multiple stable climate states separated by thresholds is a feature of many calculations. More complex three-dimensional climate models which resolve winds, currents, and cloud fields in greater detail also find that when atmospheric carbon dioxide falls below certain levels, extensive low-latitude sea ice becomes a stable outcome for Neoproterozoic-style boundary conditions. In these simulations, global glaciation is not triggered by a single mechanism, but can result from different combinations of reduced greenhouse gases, altered land surface properties, and shifts in ocean and atmospheric circulation. The rocks that record cryogenian glaciation are consistent with climates that have crossed such thresholds. Glacial deposits assigned to the Sturtian event are found on most of the major Proterozoic continents and occur at paleolatitudes that include the tropics. The duration of this glaciation, constrained by radiometric ages and sediment accumulation, spans tens of millions of years, indicating that the resulting climate mode is long-lived, rather than a brief fluctuation. In some regions, thick successions of diamictites and associated faces suggest active ice sheets and tidewater glaciers that persist over substantial intervals, while in others, thinner or more intermittent deposits may reflect local conditions or incomplete preservation. Widespread evidence of grounded ice near sea level at low latitudes implies that thick ice occupies positions far from the poles, a geometry more readily produced by a strongly glaciated climate than by modest cooling. At the same time, certain sedimentary and geochemical features have been interpreted as possible signs that not all ocean surfaces are permanently sealed by thick, stagnant ice. Patterns in banded iron formations, carbonate faces, and microfossil distributions have been used to argue for the presence of areas with thinner ice, seasonal openings or limited open water, leading to the concept of slush ball states, in which most of the planet is ice-covered, but narrow belts or isolated regions remain partially ice-free. Climate models can reproduce both nearly complete snowball solutions and strongly glaciated but not fully frozen states, depending on the assumed greenhouse gas concentrations, cloud feedbacks, and sea ice properties. In some simulations, thin equatorial sea ice overlies liquid water, allowing limited exchange of gases and nutrients between the ocean and atmosphere, while still keeping the overall planetary albedo high. Other simulations find stable hard snowball conditions with thick ice everywhere at the surface, which would require very high levels of carbon dioxide to terminate, because degassing must accumulate greenhouse gases over long intervals before the outgoing long-wave balance permits melting. The critical carbon dioxide levels needed to escape a hard snowball state in these models can be many times higher than those of the pre-industrial atmosphere, reflecting the strong cooling effect of a bright ice-covered planet. Within this framework, the feedbacks that tip Earth into global or near-global ice involve not only ice-albedo interactions, but also changes in clouds, water vapor, and atmospheric circulation. As surface temperatures fall, the atmosphere holds less water vapor, which weakens the greenhouse effect associated with this gas and further cools the planet. Reduced water vapor also tends to decrease the formation of certain cloud types that trap outgoing infrared radiation, although changes in low cloud cover that strongly reflect sunlight can either enhance or moderate cooling depending on their distribution. Snow and ice cover on continents alter surface roughness and can influence wind patterns, which in turn affect the transport of heat and moisture. Expanding sea ice, especially when it becomes thick and less mobile, restricts the exchange of heat and gases between the ocean and atmosphere, allowing the surface ocean to equilibrate to colder states, even as deeper waters continue to circulate slowly. At high latitudes, the growth of grounded ice sheets changes the mass distribution on the surface, potentially affecting Earth's rotation and precession cycles on long time scales, although the influence of these changes during the Cryogenian remains under study. The combined effect of these processes is to strengthen the stability of the cold climate once it has formed, making it more resistant to modest perturbations in solar input or greenhouse gas levels. For example, if volcanic eruptions inject additional carbon dioxide into the atmosphere during a snowball interval, the immediate warming may be small because the high reflectivity of the surface and the low water vapor content of the atmosphere limit the system's sensitivity. Only when greenhouse gas concentrations rise to much higher values accumulated over millions of years of continuous degassing, with limited weathering, do climate models predict that the energy balance will shift back toward a state with surface melting. In the meantime, the positive feedbacks associated with ice albedo and the structure of the atmosphere help maintain an extensive ice cover that persists over the time spans recorded by Cryogenian glacial sequences. The first major Cryogenian ice age recognized in the rock record is the Sturtian glaciation, an interval that begins roughly 717 million years ago and ends around 660 million years ago, lasting on the order of several tens of millions of years. Geochronological work using uranium-lead dating of volcanic and sedimentary units, bracketing glacial deposits, places the onset of Sturtian ice in multiple basins at nearly the same time, indicating that the transition into this glacial state is not purely local. Glacial deposits of broadly similar age appear on most of the large Proterozoic continents, including the ancestors of present-day North America, South America, Africa, Australia, Antarctica, and parts of Asia. In many regions, these deposits occur within thick sedimentary successions that were previously dominated by non-glacial shallow marine carbonates and siliciclastic rocks. The shift from relatively uniform carbonate platform deposition to the appearance of diamictites, dropstones, and other ice-related facies marks a significant change in sedimentary environment that is consistent with the arrival of grounded ice at or near sea level. Where paleomagnetic data are available, measurements of remnant magnetization in associated volcanic and sedimentary units show that some of these Sturtian glacial strata are laid down at low paleolatitudes, in some cases within a few tens of degrees of the paleoequator. This combination of low latitude positions and clear glacial indicators supports the view that during the Sturtian event, ice sheets extend far beyond polar regions and reach into areas that normally host warm ice-free conditions. In many successions, Sturtian glacial deposits are thick and internally complex. Basal diamictites composed of poorly sorted mixtures of clay, silt sand, and larger clasts rest directly on older, sedimentary or volcanic rocks, sometimes with striated or faceted clasts that record abrasion at the base of moving ice. Above these repeated intervals of massive or stratified diamictites, Interbedded sandstones and mudstones can appear together with layers that show dropstones deforming underlying lamination. Some sequences also contain rhythmites or finely laminated mudstones interlayered with dropstones, which suggest that ice rafts carrying pebbles and cobbles melt and release their load into relatively quiet water. The vertical stacking of these faces implies that ice advances and retreats, or that different parts of an ice margin shift position over time rather than a single monotonous glacial environment. In a few basins, iron-rich chemical sediments, including banded iron formations, are interlayered with or closely associated with Sturtian glacial strata. These deposits indicate that during at least part of the Sturtian interval, the ocean contains significant amounts of dissolved ferrous iron that can be oxidized and precipitated in layered form. The presence of banded iron formations within a glacial context suggests that deep waters beneath ice are chemically stratified and that periodic oxygenation events reach iron-rich layers, perhaps linked to changes in circulation ice cover or surface productivity. Laminated iron formations recording regular variations in layer thickness have been interpreted as preserving orbital scale climate cycles, implying that even under extensive ice, the ice sheets and associated environmental conditions respond to changes in Earth's orbit and rotation parameters. Taken together, these lines of evidence portray the Sturtian event as a long-lived extensive glaciation that affects both land and sea at many latitudes. The combination of global distribution low-latitude indicators and synglacial chemical sediments is one of the main reasons why the Sturtian glaciation figures prominently in discussions of Snowball Earth climates. In this context, the term Snowball Earth refers to a climate state in which most or all of the ocean surface is covered by thick sea ice. Continental ice sheets are widespread and planetary. Albedo is high enough to maintain low temperatures for millions of years until greenhouse gas accumulation drives deglaciation. Some interpretations of the Sturtian record view it as an example of such a nearly fully ice-covered state, emphasizing the ubiquity of glacial deposits, the presence of banded iron formations that imply limited deep ocean oxygenation, and the long duration inferred from radiometric ages. Other interpretations point to features that could indicate zones of thinner ice or restricted open water at low latitudes, such as faces that resemble wave-influenced shallow marine environments, or evidence for continued if reduced biological activity in surface waters. In this alternative view, the Sturtian climate corresponds more closely to a strongly glaciated slush ball-style Earth, with equatorial belts of thin ice, or seasonal openings surrounded by thick persistent ice elsewhere. Climate models can be configured to match either style of solution, depending on assumptions about greenhouse gas concentrations, cloud properties, sea ice dynamics, and the efficiency of heat transport by the ocean and atmosphere at Neoproterozoic boundary conditions. Geological constraints help narrow the plausible range by setting minimum requirements on ice extent and duration. For example, the thickness and extent of diamictite packages, the continuity of glacial facies across basin-scale distances, and the presence of low-latitude indicators all require that large ice sheets remain stable for long periods and that they regularly reach near sea level outside polar regions. The long time span between the best-dated onset and termination horizons implies that once the Sturtian glaciation begins, the climate remains in a cold, ice-dominated mode for tens of millions of years, rather than oscillating rapidly back and forth between glacial and non-glacial states. Within this interval, internal variability associated with ice dynamics, orbital forcing and ocean circulation may still cause changes in ice sheet thickness, grounding line position, and sea ice cover. But the overall character of the climate stays strongly glacial, as recorded in the rock successions that accumulate during this time. Between the termination of the Sturtian glaciation and the onset of the Marinoan glaciation, Earth passes through a cryogenian non-glacial interval that is short in geological terms but complex in its environmental character. Radiometric ages from volcanic ashes and other datable horizons, bracketing glacial and non-glacial units, indicate that the Sturtian Ice Age ends near 660 million years ago, and that the Marinoan glaciation begins somewhere between about 650 and 640 million years ago, so the intervening non-glacial interval most likely spans on the order of 10 to 20 million years. In stratigraphic sections on multiple paleocontinents, thick Sturtian diamictites and associated glacial faces are overlain by successions of predominantly non-glacial rocks, including shallow marine carbonates, fine-grained siliciclastics, and mixed carbonate siliciclastic units. These overlying formations commonly record the return of an active hydrological cycle at low and middle latitudes, with evidence for normal wave and storm processes on continental shelves, the development of tidal and deltic systems, and renewed carbonate platform growth in some regions. In a number of basins, the transition from Sturtian glacial deposits into these non-glacial units is marked by a change from poorly sorted ice-influenced sediments to better sorted sandstones, siltstones and limestones that show bedding, cross-stratification, and other structures typical of open water deposition. Regional marine transgression during this interval floods low-lying continental interiors and extends shallow seas across broad areas of the supercontinent fragments, so that large parts of the land surface that were previously overridden by ice sheets become submerged beneath epicontinental seas. The global carbon isotope record across this interglacial interval shows pronounced variability. Carbonate rocks formed after the Sturtian termination, but before the Marinoan onset display substantial departures from typical Proterozoic carbon isotope values in some cases, including large negative excursions that indicate shifts in the balance between organic carbon burial and the exchange of carbon between surface reservoirs and the deeper ocean. Detailed studies of coeval carbonate formations on different crustal blocks reveal that not all basins share identical carbon isotope signatures, suggesting that local or regional processes influence the isotopic composition of seawater in addition to any global signals. In certain areas, carbonate successions with unusual isotopic values are interbedded with siliciclastic layers that reflect changes in sediment supply and accommodation space as tectonics and sea level jointly control basin evolution. The combination of high-amplitude carbon isotope excursions, variable facies patterns, and the relatively short duration inferred from geochronology points to a carbon cycle that is adjusting rapidly to the loss of extensive ice cover and to continuing tectonic and magmatic activity, rather than a return to a long steady background state. Evidence from trace metal concentrations, isotopic tracers, and other geochemical proxies in non-glacial cryogenian formations indicates that deep ocean waters during this interval remain largely poorly oxygenated. Records of elements such as molybdenum, uranium, and iron, together with their isotopic compositions, suggest that widespread anoxia or euxinia persists in many basins even while surface waters experience more typical open ocean conditions. In some successions, data from organic biomarkers and microfossils show that eukaryotic plankton, including relatively complex protists such as ciliates, inhabit surface or near-surface waters in the time between the two major glaciations, indicating that marine ecosystems with diverse unicellular eukaryotes are present under these chemical and physical conditions. Other studies report possible sponge-related biomarkers and small simple body fossils from rocks that are either within this interglacial interval or close to its end, implying that early Metazoan-grade organisms may also occupy some marine environments before the Marinoan Ice Age begins, although the precise ages and environmental settings of these occurrences continue to be refined. Sedimentary facies patterns in several basins show alternations between carbonate-dominated intervals and more silica-clastic-dominated intervals, which can be interpreted as reflecting shifts in relative sea level sediment supply and basin subsidence as rifting and passive margin development proceed. In some regions, tidal flat deposits, shallow subtidal carbonates, and deeper water slope or basinal sediments are all represented within the interglacial succession, illustrating that the full range of shelf-to-basin environments redevelops once major ice sheets retreat. Climatic conditions during this non-glacial window are generally interpreted as significantly warmer than during the preceding Sturtian glaciation, with ice confined to higher latitudes or to upland regions, but they do not necessarily match the warmest states of earlier Proterozoic time. The same tectonic and geochemical factors that help drive the Sturtian glaciation, including continental breakup, large igneous province emplacement, and weathering and evolving ocean redox structure, continue to influence the Earth system, and geochemical and sedimentological records show that the oceans and atmosphere are still undergoing substantial reorganization, while surface ice is absent from most low-latitude settings. Within this framework, the Cryogenian non-glacial interval represents a period in which open oceans, active carbonate platforms, and diverse microbial and eukaryotic communities coexist with deep waters that remain largely low in oxygen and with a carbon cycle that displays large, rapidly changing excursions in its long-term isotopic indicators. In many cryogenian successions, the Marinoan glaciation forms the upper major glacial unit stratigraphically above the Sturtian deposits and below distinctive postglacial carbonates. Radiometric ages from volcanic ash beds in Marinoan successions and from zircons in associated units show that this younger glaciation ends near 635 million years ago. Constraints on its onset are less precise, but available dates indicate that it begins after the Cryogenian non-glacial interval that follows Sturtian deglaciation, and that its total duration is at least several million years. Marinoan age glacial deposits occur on most known Neoproterozoic paleocontinents. Thick glaciogenic successions of this age are recognized in what are now South China, Namibia, Australia, Brazil, Canada, Svalbard and other regions. In multiple basins, these deposits rest unconformably or disconformably on older non-glacial sedimentary rocks, and are themselves overlain sharply by later carbonate formations. The wide distribution of Marinoan glacial faces, together with their consistent stratigraphic position below a characteristic set of cap carbonates, indicates that this glaciation is a widespread coherent event rather than a collection of unrelated regional cold periods. Paleomagnetic measurements on some Marinoan successions place the glacial deposits at low paleolatitudes, implying that ice again reaches into tropical regions. These low-latitude indicators, combined with the scale and global spread of Marinoan diamictites, are central reasons why this event is grouped with the Sturtian as one of the two main Cryogenian snowball-style glaciations. Sedimentological and geochemical features within Marinoan glacial successions share certain properties with Sturtian deposits, but also show differences that provide additional information about climate state. Many Marinoan sections begin with basal diamictites that contain angular to rounded clasts of varied lithologies in a fine-grained matrix interpreted as tills or mass flow deposits related to glaciers advancing over previously deposited strata. Striated clasts and striated or polished bedrock surfaces beneath these diamictites record abrasion beneath grounded ice. Higher in the sequences into bedded diamictites, sandstones and finer-grained mudstones indicate fluctuating depositional processes along ice margins in proglacial marine settings or beneath floating ice shelves. Dropstones deforming underlying laminations demonstrate that ice roughs carrying coarse debris melt and release their load into quieter water. In some Marinoan basins, rhythmites or graded beds are present which may reflect repeated delivery of sediment from seasonal meltwater flows or from variations in ice advance, and retreat on timescales shorter than the overall length of the glaciation. Chemical sediments, including banded iron formations and manganese-rich layers, are less common in Marinoan than in Sturtian successions, but do occur in certain areas. Where present, these iron-rich units indicate that portions of the ocean remain chemically stratified and contain reduced iron during the younger glaciation. Above the uppermost diamictites, a distinctive suite of cap carbonates often appears. These carbonate units are typically thin compared with the full thickness of the glacial succession, yet are laterally extensive and directly overlie glacial deposits with little or no intervening clastic sediment. They display unusual sedimentary structures such as large ripple-like bedforms, polygonal surface features, and fans of carbonate crystals as well as carbon isotope values that differ from typical background marine carbonates. The close repeated association of cap carbonates with Marinoan and other cryogenian glacial terminations indicates that they form during a distinct phase of postglacial ocean and atmosphere chemistry that follows intervals of extensive ice cover. Interpretations of the Marinoan climate state draw on this sedimentary and geochemical evidence together with climate modelling. One end-member view treats the Marinoan as a full Snowball Earth interval in which thick sea ice covers nearly all ocean surfaces and grounded ice sheets extend across most continental areas. Under this interpretation, low-latitude glacial deposits widespread cap carbonates, and the requirement for very high carbon dioxide levels to end glaciation are cited as lines of support. In a contrasting view, the Marinoan is instead a strongly glaciated but not fully globally frozen state, with bands of thinner sea ice or restricted open water at some low latitudes. Observations used in favour of this slush ball-style scenario include sedimentary facies that seem to record wave or storm activity in shallow marine settings during the glaciation, and isotopic or trace element records that are interpreted to require ongoing exchange between the atmosphere-surface ocean and deeper waters. Climate models configured with Neoproterozoic boundary conditions can produce both types of solutions depending on the assumed greenhouse gas concentrations, cloud properties and sea ice behaviour. Simulations with thicker stagnant sea ice and limited ocean heat transport favour nearly complete ice cover, while models that allow more dynamic sea ice flowing sea glaciers or enhanced equatorial upwelling can sustain regions with thinner ice or intermittent openings even when global mean temperatures are far below freezing. Geological constraints such as the distribution and thickness of Marinoan glacial deposits, the presence or absence of periglacial features, and the character of associated chemical sediments are used to evaluate which family of model solutions is more consistent with the rock record. Independent constraints on the duration and character of Marinoan ice come from cyclostratigraphic analyses and from studies of glacial isostatic adjustment recorded in sedimentary successions. In some Marinoan basins, rhythmic layering within glacial and immediately post-glacial deposits can be matched to orbital cycles yielding estimates of glaciation lengths of several million years. Other recent work that combines sediment thickness, flexural response of the lithosphere to changing ice loads and sea level indicators suggests that in at least some areas, grounded ice margins remain relatively stable in position over spans of millions of years, with only limited vertical motion of the grounding line. These findings are consistent with a climate state in which large ice sheets and sea ice cover are sustained by a persistent global energy balance, while the diversity of phases between basins points to regional variation superimposed on the global signal of very extensive low-latitude glaciation. On the scale of individual continents during the Cryogenian glaciations, ice accumulates preferentially on uplands and interior plateaus of the Rodinia fragments, forming large grounded ice sheets that flow under their own weight towards surrounding lowlands and continental margins. Where snowfall exceeds melt over many years, thick ice bodies grow, develop internal flow lines, and organize into ice divides in interior regions from which ice streams move outward toward zones of net loss. The dynamics of these cryogenian ice sheets are governed by the same physical principles that operate in more recent glacial intervals. Ice deforms slowly as a viscous material basal sliding occurs where pressure melting and the presence of water at the bed allow decoupling from the substrate, and frictional resistance and bed roughness influence flow speeds and patterns. In high elevation or cold interior areas, basal temperatures may remain below the pressure melting point, so that ice is frozen to its bed and erosion is limited. In lower, thicker or more coastal sectors, basal melting and sliding are more likely, enhancing erosion and the evacuation of sediment by fast-flowing ice streams. Sediment delivered to the bed of these ice sheets is transported toward their margins, where it is deposited as tills beneath stationary ice, as grounding zone wedges at the point where grounded ice begins to float, or as subaqueous mass flows and gravity-driven deposits in deeper water. The presence in cryogenian successions of massive diamictites, stratified diamictites and associated facies with features such as sheared matrices, lodgement clests and abrupt transitions from non-glacial to glacial facies, is consistent with these types of ice sheet behavior at marine margins. In some basins, laterally extensive diamictite units with internal architectural elements suggest repeated advance and stillstand of grounding lines across continental shelves, implying that once large ice sheets reach shallow marine environments, they can occupy those regions for long periods while their fronts adjust to changes in ice flux sea level and subglacial topography. Where grounded ice from continental interiors flows across coastlines into standing water, floating ice shelves are able to form. In these settings, the ice sheet thins seaward until its weight is balanced by seawater buoyancy, producing a transition from grounded ice to freely floating ice. The zone over which this transition takes place, the grounding zone, can in principle leave characteristic signatures in the sedimentary record, including wedges of sediment, thickening seaward from the grounding line, and changes from more massive subglacially deformed diamictites landward to more stratified waterworked diamictites and related facies seaward. Observations from cryogenian glaciogenic successions in different regions show patterns that resemble these features, and comparisons with well-studied younger glaciated margins provide a physical framework for interpreting them. Floating ice shelves themselves would have extended tens to hundreds of kilometers offshore, in some sectors fed by ice streams draining the interior and losing mass by basal melting, and by carving of icebergs along their seaward edges. Beneath the shelves, ocean water constrained by topography and modulated by tidal and density-driven circulation can melt ice at the base, transport heat and salt, and redistribute sediments released from the ice. Because sea level during cryogenian glaciations is influenced both by the growth and decay of continental ice, and by longer-term tectonic changes in basin depth. The position and thickness of ice shelves over continental shelves and slopes would have responded to a combination of climatic and geological controls. Along some margins, grounded ice may have advanced all the way across the shelf to near the shelf edge, whereas in other areas shelves and floating tongues may have persisted above deeper basins with grounded ice only closer to shore. Offshore from the continental margins, sea ice and snow cover spread over the open ocean. In climate states approaching hard snowball conditions, numerical models and theoretical analyses indicate that this sea ice can reach great thicknesses, potentially on the order of hundreds of meters or more, and behaves as a viscous medium that can flow slowly under its own weight. Under these circumstances, ice initially forming in high and middle latitudes can thicken and spread equatorward as a sea glacier driven by surface mass balance and by gradients in ice thickness. Where sea ice remains thinner, or where upwelling of relatively warm subsurface water occurs, local thinning or limited openings may develop, but the overall pattern in strongly glaciated states is one of very extensive multi-year ice cover. The mechanical properties of thick sea ice combined with wind stress and ocean drag influence the formation of leads ridges and pressure features, though their detailed geometry in cryogenian oceans is not preserved directly and must be inferred from models and analogy with more recent polar seas. In climate scenarios closer to slushball conditions, sea ice may still be widespread, but somewhat thinner on average with possible narrow belts or regions, at low latitudes where seasonal melting or dynamic thinning allows partial exposure of the ocean surface. In either case, the distribution of sea ice exhibits strong regional variation, controlled by prevailing winds patterns of ocean circulation, and the arrangement of continents and basins that shape current pathways. Near the coasts of glaciated continents, latent heat, polynyas, can form where persistent offshore winds or the circulation beneath ice shelves remove newly formed sea ice and maintain open or thin ice-covered water adjacent to the ice front, even as surrounding areas remain more solidly frozen. Such features are important for local heat loss from the ocean, for the production of cold saline water that can sink and contribute to deep circulation, and for the redistribution of sea ice and icebergs away from coastal zones. In the interior of the ocean basins, especially under thick continuous ice, direct exchange between surface waters and the atmosphere is greatly restricted, so that ocean circulation and geothermal heating become dominant in setting the thermal and dynamical state of the water column beneath the ice. The combined pattern of large grounded ice sheets on land ice shelves along many continental margins and extensive sea ice and sea glaciers over the ocean defines the geometry of the cryogenian cryosphere at the scale of individual continents and their surrounding basins. During cryogenian glaciations, the global ocean lies beneath a continuous or near-continuous cover of sea ice and snow, forming a distinct sub-ice environment that operates under boundary conditions very different from those of an ice-free surface. The sea ice cover insulates the liquid ocean from direct contact with the atmosphere, greatly reducing exchanges of heat moisture and gases across the air-sea interface. Conductive heat loss through the ice still occurs, especially where ice is thinner, but most incoming solar radiation is reflected, and only a small fraction penetrates through snow and ice layers into surface waters. Geothermal heat from Earth's interior delivered mainly through the seafloor, and focused at mid-ocean ridges and hydrothermal systems becomes a key source of energy for the ocean, together with the latent heat exchanges associated with freezing and melting at the base of the ice cover. As sea ice forms, it rejects salt into the underlying water, increasing salinity and density in near-surface layers. When basal melting occurs, relatively fresh water is added back. These opposing fluxes, together with geothermal input, drive convective motions that contribute to the vertical mixing of the sub-ice ocean. Numerical simulations of globally glaciated oceans show that under such conditions, circulation patterns differ from those of a modern open ocean. With the surface effectively sealed, wind-driven currents are weak, and the main drivers of motion are geothermal heating from below, cooling and brine rejection near the base of the ice, and slow diffusion of heat and salt. In many model configurations, these processes produce a turbulent but relatively well-mixed deep ocean, with only modest vertical stratification in temperature and salinity compared with open ocean states. Some studies find strong narrow jets and overturning cells concentrated near the equator, where variations in ice thickness and geothermal flux intersect with the Coriolis effect, while higher latitudes exhibit slower, more uniform flow. In these simulations, dense water formed beneath regions of intense freezing sinks and spreads along the seafloor, while slightly warmer, less dense water rises elsewhere, establishing a slow, global scale, overturning circulation that operates beneath the ice cover. The rate of this circulation is limited by the weak surface forcing, so water masses can reside at depth for long intervals, allowing chemical traces and dissolved species to accumulate or evolve. Over time, repeated brine rejection events during sea ice growth tend to increase the average salinity of the ocean, especially if net ice volume increases, and this salinity structure feeds back on circulation by influencing density gradients. The geometry and behavior of the ice cover modulate where and how strongly the sub-ice ocean interacts with the atmosphere. In many snowball-style scenarios, sea ice is thickest near the equator, where the sea glacier formed by slowly flowing ice converges, and somewhat thinner toward higher latitudes where conductive heat loss to the cold atmosphere is more efficient. Differences in thickness affect the rate at which heat can escape from the ocean, and also influence the likelihood of local thinning, cracking, or opening. Around some continental margins and topographic obstacles, winds blowing off the ice sheets can drive sea ice away from fixed boundaries, creating narrow zones of open water or thin ice known as coastal or latent heat polynyas. In these regions, new ice forms repeatedly as cold air cools exposed seawater. The ice is then pushed away, leaving open water behind. Each cycle of freezing rejects salt, forming dense brine that sinks and spills off continental shelves into deeper basins, helping to ventilate the sub-ice ocean and maintain deep water formation despite overall ice cover. Modern polynyas in the Antarctic act as important sites of sea ice production and dense water formation, and similar processes can operate in cryogenian oceans, although with different absolute fluxes and geometries. In slush ball-style configurations with somewhat thinner low latitude ice, additional polynyas or seasonal openings may arise in equatorial belts, where ocean dynamics or upwelling brings slightly warmer water into contact with the base of the ice. These openings allow limited exchange of gases between the ocean and atmosphere, and provide locations where aerosols, volcanic gases, and possibly dust can enter the ocean directly. Above the ice, the atmosphere adjusts to the presence of a highly reflective low-heat capacity surface. With little open water, evaporation is strongly reduced, and atmospheric water vapor content declines relative to warmer ice-free climates. Lower humidity weakens the water vapor greenhouse effect and changes cloud formation patterns. General circulation models configured for snowball conditions show that the small thermal inertia of the ice-covered surface amplifies seasonal and diurnal temperature variations in low latitudes and alters the structure of large-scale circulation cells. In some experiments, the annual mean tropical overturning circulation reverses sense compared with modern Earth, producing subsiding relatively dry air near the equator and rising motion in off-equatorial belts. Under such a pattern, snowfall and frost accumulation are enhanced in subtropical or mid-latitude regions, while the equatorial belt receives little net precipitation, a configuration that favours net snow and frost growth away from the equator where ice albedo feedback is still effective. Over and around large continental ice sheets, cold dense air forms near the surface and flows downslope under gravity as katabatic winds. These winds can attain high speeds as they descend from interior plateaus to coastal margins, especially where topography funnels flow through valleys. On reaching the coast, katabatic winds push sea ice away from the shoreline, contributing to the formation and maintenance of latent heat, polynyas, and enhancing air-sea heat fluxes locally. The same winds loft snow and fine sediment into the lower atmosphere, transporting dust and other particles over considerable distances before they settle out onto the ice surface or into open water regions. Dust and aerosol loading in a cryogenian atmosphere depend on both source availability and wind patterns. As glaciation expands, many potential dust sources become covered by ice and snow, limiting emission from those areas. However, zones of strong sublimation exposed bedrock in ice-free or thinly covered regions and volcanic terrains still supply particulate material. Model experiments that couple dust emission to surface conditions suggest that as snow cover becomes more widespread, globally total dust emission may decline, but remaining active regions can still produce significant dust fluxes relative to the reduced hydrological cycle. Deposition of dust on the ice surface, particularly in low and middle latitudes where sublimation dominates over snowfall, can locally lower surface albedo by darkening the snow and ice. This effect is spatially heterogeneous and depends on how quickly fresh snow can bury dust layers. Under very dry conditions, exposed dusty surfaces may persist for extended periods. Volcanic eruptions inject gases and ash into the atmosphere above and around ice sheets, adding short-lived aerosols that influence cloud droplet formation and radiative transfer. In the thin, cold air of a snowball-type atmosphere, these particles can remain aloft long enough to spread widely before gravitational settling brings them down. Storm systems in this environment form along temperature gradients associated with contrasts between regions of different surface elevation, ice thickness, and air mass properties. With limited latent heat release from condensation and a reduced global hydrological cycle, storms carry less moisture than in warm climates, but they still organize into waves along mid-latitude jets and other preferred bands. Their winds reshape the surface of the snow and ice, transport fine particles, and modulate heat fluxes where they interact with polynyas and thin ice zones. Together, the sealed but circulating sub-ice ocean, the dynamic yet moisture-limited atmosphere, and the network of polynyas and ice thickness variations create a coupled system in which heat, salt, and momentum continue to move across the planet, even while the surface remains dominated by ice and snow. Geological, paleontological, and molecular evidence together indicate that life continues through the cryogenian glaciations, even as large parts of Earth's surface are covered by ice. Microfossil assemblages from rocks of cryogenian and immediately pre-cryogenian age show that bacteria, cyanobacteria, and a range of eukaryotic microorganisms are already present before full glaciation and reappear after it. Acritarchs, which are organic walled microfossils, interpreted mainly as resting stages of planktonic eukaryotes, occur in Neoproterozoic successions, and include forms that survive across glacial boundaries in some regions. In addition, certain carbonate and shale units deposited between or close to the glaciations contain biomarkers and fossils of unicellular eukaryotes such as green algae and other protists. These observations show that diverse microbial and eukaryotic lineages are already established in the oceans by the time the Cryogenian ice ages begin. Their continued presence in strata deposited after the glaciations implies that they persist somewhere during the long intervals of extensive ice cover. However, the sedimentary record from the glacial intervals themselves is sparse in easily recognizable fossils, both because many glacial deposits are coarse-grained and because preservation under subglacial or periglacial conditions is limited. As a result, information on cryogenian life during peak glacial conditions relies heavily on indirect clues from geochemistry and on analogies with modern ice-associated ecosystems, together with theoretical models of possible refugia. These refugia are environments in which liquid water, nutrients and energy are available despite surface ice, allowing small but active populations of microorganisms and potentially simple multicellular organisms to survive. One class of proposed refugia lies within and beneath the sea ice cover. Modern polar sea ice contains networks of microscopic brine channels and pockets that remain liquid at temperatures well below the freezing point of normal seawater because the brine is highly saline. These microenvironments host dense microbial communities, including photosynthetic algae and bacteria in present-day Arctic and Antarctic ice. In cryogenian-style oceans, sea ice can grow much thicker than in the modern world, but modelling studies and physical arguments indicate that brine drainage, grain boundary processes and thermal gradients still create internal liquid pathways and pockets. In scenarios with thinner low-latitude ice, more light can penetrate to the uppermost part of the ocean, so photosynthetic microorganisms may inhabit brine channels and the underlying water column, especially near regions where ice is seasonally thinned or where polynyas and leads provide access to the atmosphere. In thicker ice regions, photosynthesis is more strongly limited, but chemotrophic microorganisms that use reduced chemical species such as ferrous iron, sulfide or methane can occupy brine channels and the sub-ice water column, where these substrates are supplied from below. Another type of sea ice-related refugium involves cryoconite holes and ponds on the ice surface. In modern glaciers, wind-blown dust, volcanic ash, and organic particles accumulated on the surface can absorb solar radiation and locally melt depressions that hold liquid water during the warmest part of the year. These depressions support microbial consortia that exploit both sunlight and nutrients concentrated in the meltwater. During cryogenian glaciations, dust fluxes, volcanic particles, and other aerosols still reach the ice surface, and similar processes may create supraglacial melt pools in regions where seasonal or local conditions allow melting. These pools would be small in area compared with the total ice cover, but could host active communities during the intervals when liquid water persists. Subglacial environments form another major group of potential refugia. Under thick ice sheets, geothermal heat from Earth's interior and the pressure dependence of the melting point of ice can generate basal meltwater, even when surface air temperatures are far below freezing. This meltwater can collect in films channels and larger subglacial lakes at the interface between ice and bedrock. Modern analogues beneath the East Antarctic ice sheet show that such lakes can store liquid water for long periods, interact with underlying sediments, and exchange solutes and microorganisms with subglacial drainage systems. During the cryogenian, similar processes can maintain extensive subglacial hydrological networks beneath continental ice sheets and perhaps beneath floating ice shelves near grounding lines. Chemical reactions between meltwater crushed bedrock and reduced minerals supply solutes including iron, manganese, sulfur species, and dissolved inorganic carbon, which can sustain chemolithotrophic microbial communities independent of sunlight. Periodic drainage events may flush subglacial waters into the ocean, dispersing microorganisms and nutrients more widely beneath the ice cover. In tectonically active regions, subglacial systems can connect to hydrothermal or volcanic environments, adding heat and reduced chemical species to the available energy sources. Hydrothermal vents and cold seep systems on the seafloor represent additional refugia for life during global or near-global glaciation. Mid-ocean ridges, back-arc basins and volcanic arcs continue to operate throughout the Cryogenian, releasing hot chemically enriched fluids into the deep ocean. Modern vent communities in ice-free oceans are anchored by chemoautotrophic microorganisms that oxidize reduced compounds such as hydrogen sulfide and methane to fix carbon. Similar metabolic strategies can function beneath an ice-covered ocean, where access to sunlight is limited or absent. Geophysical and geochemical evidence indicates that seafloor hydrothermal circulation remains active in Neoproterozoic time, so it is reasonable to expect that microbial ecosystems exploiting these environments continue during Cryogenian glaciations. Cold seeps where hydrocarbons or other reduced fluids leak slowly through sediments offer further sites for chemosynthetic life. In both cases, the overlying ice cover alters circulation and sedimentation patterns, but does not remove the underlying energy sources. Ice-covered lakes and inland seas, whether purely freshwater or brackish, provide another class of refugia, especially on or near continents. Lakes can form in tectonic depressions, rift basins, or regions dammed by ice or topography. When covered by ice and snow, these water bodies receive less light and are more strongly stratified than open lakes. Yet modern analogues in polar regions show that photosynthesis and microbial activity can persist in their upper water columns where some light penetrates. In deeper layers, redox gradients support diverse microbial metabolisms as organic matter settles and is decomposed. During the Cryogenian, lakes in tectonically active or volcanically heated regions may remain partially ice-free for part of the year, or may sustain thin ice covers compared with surrounding ocean basins, thereby offering relatively favourable conditions for planktonic and benthic life. In more strictly snowball-style scenarios, these lakes are fully ice-covered, but can still host microbial ecosystems that are adapted to low temperature and low light. On land and at the margins of ice sheets, microhabitats in snow, ice and rock offer additional possibilities. Snow algae and other microorganisms are known today from seasonal snowpacks and glacier surfaces, where they tolerate intense radiation, freeze-thaw cycles and nutrient scarcity. During the Cryogenian, similar organisms may occupy illuminated snow surfaces, especially in lower latitude or lower elevation settings, where light levels are higher and seasonal warming is greater. Endolithic communities in which microorganisms inhabit pore spaces or microcracks within translucent rocks provide another refuge. These communities benefit from shielding against ultraviolet radiation and temperature extremes while still receiving enough light for photosynthesis. Glacial environments also expose fresh rock surfaces through erosion, creating new habitats of this kind. Some researchers have suggested that such glacial and periglacial habitats could have been important for the evolution of specific algal groups that later colonize land, although the exact timing and pathways remain under discussion. A final category of refugia involves regions where the ocean surface is locally ice-free or covered by thin, seasonally variable ice. In slushball-type models, low-latitude belts of thin sea ice or intermittent open water persist even at the height of glaciation. In snowball-style models with thicker ice, coastal and latent heat, polynyas near the margins of large ice sheets can provide limited areas of open water or newly formed thin ice over longer intervals. These locations admit more light to the upper ocean, allow direct gas exchange between ocean and atmosphere and can support photosynthetic plankton as well as microbial and possibly simple multicellular life in the underlying water column. Sedimentary and geochemical evidence for continued biological productivity and for dynamic nutrient and redox cycling in some cryogenian basins is often interpreted as indirect support for at least some open or thin ice-covered surface waters. The detailed size, number, and geographic pattern of such regions remain uncertain, but they offer physically and biologically plausible sites where marine ecosystems can persist and recover during long glacial episodes. In the outcrop record of cryogenian glaciations, some of the most direct indicators of ice activity at local scales are glacial sediments preserved as lithified tills, diamictites, and related facies. A till is an unsorted or poorly sorted mixture of clay, silt sand, and larger clasts deposited directly by glacial ice. When such material becomes compacted and cemented into rock, it is called a tillite. Many cryogenian diamictites are interpreted as lithified tills of this kind, although the term diamictite itself is purely descriptive and refers only to a poorly sorted rock with a wide range of grain sizes. In cryogenian successions, glacial diamictites often occur as thick, massive units, resting sharply on older strata with erosional bases and striated or facetted clasts that indicate abrasion against bedrock beneath moving ice. The matrices of these rocks can be rich in rock flour, the fine material produced when glaciers grind their beds, and clasts may show preferred orientations or fabrics that record ice flow directions. In some basins, lodgement tills which are deposited beneath actively sliding ice can be distinguished from melt-out, tills which form where debris carried within or on top of ice is released as the ice melts. Lodgement tills tend to be more compacted and may show strong deformation structures, whereas melt-out tills often have less compacted matrices and a more chaotic internal arrangement. Cryogenian diamictites also appear in stacked sequences in which massive beds alternate with stratified or graded units containing drop stones and finer grained layers. These successions record a combination of direct subglacial deposition, reworking by meltwater, and mass flows on submarine slopes as ice interacts with continental shelves and basins. Drop stones provide another key line of evidence for ice rafting in cryogenian basins. A drop stone is an outsized clast, often a pebble, cobble, or boulder, that occurs isolated within otherwise fine-grained, typically laminated sediment. In many cryogenian sections, mudstones or siltstones that were deposited in relatively quiet water show lamination that is draped or deformed below and above such clasts, indicating that the coarse fragments fell from above into soft sediment. The most straightforward mechanism for delivering these individual clasts into deep or quiet marine settings is melting of icebergs or other floating ice that carry debris derived from land. As ice rafts drift away from glaciated coasts, they release their sediment load progressively, allowing coarse clasts to rain out over large areas of the seafloor. In some cryogenian rhythmites, regular alternations of coarser and finer laminae combined with occasional drop stones suggest that sedimentation is influenced both by seasonal or orbital forcing and by intermittent iceberg discharge. However, because drop stones can also form by other processes such as mass flows or volcanic rafting, interpretations of cryogenian dropstone-bearing units rely on the broader facies context. When outsized clasts occur together with diamictites, striated clasts, and other indicators of ice, a glacial origin for the dropstones is strongly supported. In this way, local sedimentary textures help tie individual outcrops into a consistent picture of widespread ice rafting during both the Sturtian and Marinoan intervals. Glacial striations and associated bedrock features complement the information carried by diamictites and dropstones. Striations are linear grooves, scratches or polish on rock surfaces that form when debris embedded in the base of a glacier grinds against the substrate as the ice moves. In cryogenian terrains, striated pavements occur beneath or near glacial deposits, providing direct evidence that ice once flowed across those surfaces. The orientation of striations records the direction of ice motion, and their presence beneath diamictites strengthens the interpretation that overlying poorly sorted sediments are glacial in origin, rather than products of non-glacial debris flows. Other glacial erosion features such as roche-moutonnées landforms, streamlined bedrock hills and over-deepened basins are less commonly preserved in very old terrains because later deformation and erosion may remove or obscure them, but where they are documented in Proterozoic crust, they add further support for the passage of thick erosive ice. Soft sediment deformation structures, including folds, faults, and shear zones, within unlithified or partially lithified beds beneath or within glacial successions, likewise provide evidence for loading, shearing, and rapid deposition in ice-proximal environments. Together, these mechanical imprints show that cryogenian ice sheets and glaciers are capable of reshaping local landscapes and sediment piles in ways closely analogous to younger glacial systems. A central question for cryogenian research is whether these glacial sediments now exposed in many parts of the world were originally deposited at high latitudes as in more recent ice ages, or whether some formed close to the paleoequator. Paleomagnetism is one of the main tools used to address this question. As volcanic rocks cool, or as fine-grained sediments settle, and compacted magnetic minerals within them can align with Earth's magnetic field and preserve a remanent magnetization. By measuring the direction and inclination of this remanence in carefully sampled rocks, and by correcting for later tilts and deformations, researchers can estimate the latitude at which the rocks acquired their magnetization. For several cryogenian glacial successions, paleomagnetic data obtained from interbedded volcanic units' lava flows, or immediately overlying and underlying strata, indicate low paleolatitudes at the time of deposition. In some cases, inclinations correspond to positions within roughly 10 degrees of the paleoequator. When such estimates are combined with independent evidence that the adjacent diamictites and dropstone-bearing units are glacial in origin, they imply that glaciers reached down to near sea level in tropical regions. This conclusion underpins the Snowball Earth hypothesis, which holds that during at least the Sturtian and Marinoan glaciations, ice extended from the poles to low latitudes for prolonged intervals. The interpretation of low-latitude glacial sediments is not without controversy. Some diamictites once considered unequivocally glacial have been reinterpreted as non-glacial mass-flow deposits after detailed sedimentological studies illustrating that poorly sorted sediments alone are not sufficient to demonstrate glaciation. In other instances, questions have been raised about the reliability of specific paleomagnetic results, including concerns about remagnetization events, complex deformation histories, or incomplete structural corrections. Alternative ideas such as episodes of rapid reorientation of Earth's solid exterior relative to its spin axis have been proposed in attempts to reconcile some paleomagnetic observations without invoking fully tropical ice sheets. Nevertheless, when multiple lines of evidence are taken together, including diamictites with clear glacial features, striated clasts and pavements, well-documented dropstone suites and carefully vetted paleomagnetic determinations, the case that at least some cryogenian glaciers occupy low-latitude positions remains strong. At local scale, the rocks preserve information about ice advance into marine basins, iceberg rafting into deeper waters, and erosion of bedrock by thick ice. At wider scale, the same assemblages of glacial sediments and associated data are used to reconstruct patterns of cryogenian ice extent and climate state. Chemical and isotopic records preserved in cryogenian rocks provide additional lines of evidence for the nature of these glaciations and their aftermath, complementing the physical signatures of ice in diamictites, dropstones, and striated pavements. One of the most distinctive rock types associated with cryogenian glacial terminations is the cap carbonate, a relatively thin but laterally extensive layer of limestone or dolostone that rests sharply on top of glacial deposits. In many basins, Sturtian and Marinoan diamictites are overlain without appreciable intervening clastic sediment by 2 to tens of meters of carbonate that forms a blanket across shallow platforms, ramps, and in some cases slope environments. These cap carbonates appear even where underlying successions contain little or no carbonate, and they often show abrupt planar or slightly irregular lower contacts with glacial facies rather than gradational transitions. Their internal sedimentary structures are unusual compared with more typical platform carbonates. Observed features in different regions include large, regularly spaced bed forms on bedding surfaces that resemble wave ripples at a scale of several meters, finely laminated seafloor cements that grew directly on the substrate and complexes of microbial mounds, and tubular stromatolitic structures that rise upward from basal surfaces. Some cap carbonates contain layers or nodules rich in barite, and others preserve pseudomorphs of former aragonite crystals now replaced by calcite or dolomite. These characteristics recur in broadly similar form on multiple paleocontinents, although details vary between Sturtian-style and Marinoan-style cap carbonate suites. The repeated association of such carbonates immediately above cryogenian glaciogenic deposits, together with their distinctive textures and chemical features, makes them a key marker of postglacial conditions at local and regional scales. The carbon isotopic composition of cap carbonates and associated successions records large perturbations to the marine carbon cycle during and after cryogenian glaciations. Marine carbonates deposited during much of the Neoproterozoic outside glacial intervals commonly show positive carbon isotope values relative to a standard reference consistent with substantial burial of organic carbon and a particular balance between sources and sinks in the global carbon cycle. In contrast, many cap carbonates that directly overlie Sturtian and Marinoan diamictites have carbon isotope values that are close to zero or moderately negative, sometimes several units lower than typical background values. These negative excursions are often sharp at the base of the cap carbonate and can persist through much or all of the unit, indicating that the water masses from which the carbonates precipitated carry an isotopically light dissolved inorganic carbon pool compared with earlier surface oceans. Further above, in some cryogenian and earliest Ediacaran carbonate successions, both strongly positive and strongly negative anomalies occur over stratigraphic thicknesses corresponding to intervals of several million years, suggesting continued large-scale reorganization of carbon reservoirs. In a number of sections, detailed sampling shows that isotopic values can vary systematically with facies and water depth, which indicates that local processes such as restricted circulation stratification or variable organic productivity modulate the global signal. Proposed explanations for the cryogenian and immediately post-cryogenian carbon isotope excursions include changes in the relative rates of organic carbon burial and oxidation dissolution of pre-existing evaporates, coupled with enhanced burial of sulfide minerals inputs from large pools of dissolved organic carbon in the ocean, and rapid weathering of freshly exposed glacial and volcanic rocks after deglaciation that delivers large fluxes of alkalinity and dissolved inorganic carbon to surface waters. no single mechanism yet accounts for all observed patterns in every basin, and ongoing work continues to refine how global and regional processes combine to produce the recorded isotopic variability. Cap carbonate geochemistry and stratigraphy have also been used to infer aspects of ocean chemistry and deglacial timescales, their relatively modest thickness compared with typical long-lived carbonate platform accumulations, combined with their sharp basal contact and often uniform internal isotopic profiles, are consistent with deposition during intervals that are short on geological timescales. In some recent models, a multi-stage process is proposed in which low-temperature seafloor weathering during glaciation builds up alkalinity in deep waters, then intense post-glacial continental weathering under high atmospheric carbon dioxide supplies additional alkalinity to surface waters and shallow basins, and finally mixing between glacial meltwater surface waters and deep alkalinity. Rich waters sustains further carbonate precipitation. In this framework, cap carbonates form as the ocean atmosphere system passes through a transient state after ice retreat, with precipitation rates controlled by changing saturation levels and mixing patterns rather than by a single instantaneous event. The presence of barite and particular trace element signatures in some units indicates that sulfate concentrations and redox conditions in surface waters also change during this transition. At the same time, calcium and magnesium isotope data from certain cryogenian carbonate successions show excursions that may reflect shifts in global weathering intensity, ocean acid-base balance, or the relative importance of different carbonate sinks. These records suggest that the chemical environment of the ocean during cap carbonate deposition differs significantly from that of pre-glacial times, and continues to evolve into the early Ediacaran with implications for both carbon cycling and ocean alkalinity. Banded iron formations and related iron-rich sedimentary rocks provide another chemical signal tied to cryogenian glaciations. Banded iron formations are characterized by repeated thin layers, rich in iron oxide minerals, alternating with layers of silica or other iron-poor material. They are abundant in the Paleoproterozoic record, but become rare thereafter, with the major exception of units associated with cryogenian glacial deposits. In several Sturtian age successions, iron formations occur interbedded with or closely associated with diamictites and other glacial faces. Their iron isotope compositions and trace element signatures point to deposition from waters containing significant dissolved ferrous iron under low oxygen conditions, followed by episodic oxidation that causes iron to precipitate as oxides and hydroxides. In at least one banded iron formation of this age, detailed measurements of layer thickness and cyclicity reveal patterns consistent with the imprint of orbital cycles, which implies that even during long intervals of extensive ice cover, ice sheets and ocean redox structure respond to periodic changes in insulation. In some models, prolonged sea ice cover during a snowball state limits mixing between surface and deep waters and allows ferrous iron to accumulate in the deep ocean. Periodic ventilation, or limited open water, then introduces oxidants that trigger iron precipitation. By the end of cryogenian ironstone deposition, evidence points to a change in ocean circulation and oxygenation sufficient to halt the accumulation of iron formations, marking a shift in deep water chemistry compared with the glacial interval. Taken together at local scale, cap carbonates carbon and other isotope records and cryogenian banded iron formations preserve information about the state of the ocean atmosphere system during and immediately surrounding the Sturtian and Marinoan glaciations, their stratigraphic positions, sedimentary features and chemical signatures, when considered alongside physical glacial deposits, provide a complementary perspective on how long-lived low-latitude ice cover, evolving ocean redox structure, and large shifts in carbon cycling are recorded in the rocks that formed during and just after these extreme ice ages. During the long intervals when cryogenian ice sheets and sea ice are at their maximum extent, volcanic and metamorphic degassing of carbon dioxide continues from mid-ocean ridges, volcanic arcs, large igneous provinces and zones of crustal thickening. At the same time, the usual sinks that remove carbon dioxide from the atmosphere and surface ocean are strongly reduced. Thick continental ice, extensive sea ice and cold temperatures limit the exposure of fresh silicate rocks to rainfall and liquid surface water, so continental silicate weathering operates at much lower rates than in ice-free climates. Vegetation has not yet colonized the land, and soils are thin or absent beneath many ice-covered regions, further constraining weathering. Under these conditions, the long-term carbon cycle becomes unbalanced. Degassing continues to supply carbon dioxide to the atmosphere, while the main feedback that normally consumes it is suppressed. Seafloor weathering beneath the ocean and hydrothermal circulation at mid-ocean ridges still provide some sinks, and low-temperature alteration of basalt under the ice-covered ocean may remove additional carbon dioxide, but the overall capacity of the surface system to draw down greenhouse gases is diminished compared with earlier intervals. As millions of years pass, atmospheric carbon dioxide accumulates to levels far above those of pre-glacial conditions. Geochemical modelling and constraints from cap carbonate geochemistry suggest that at the end of a full snowball-style, Neoproterozoic glaciation, carbon dioxide concentrations may reach tens of thousands of parts per million by volume or higher. Under a thick ice cover, the atmosphere and ocean are partly decoupled, so much of the accumulating carbon dioxide initially resides in the air above the ice. The radiative effect of this build-up steadily strengthens the greenhouse warming at the top of the ice cover, even as the surface remains highly reflective. At a critical point, the added greenhouse forcing becomes large enough that energy absorbed by the climate system exceeds losses from the bright ice-covered surface, and melting begins to outpace freezing at some latitudes and seasons. Numerical climate experiments for Neoproterozoic boundary conditions show that deglaciation can be initiated when carbon dioxide reaches values at which the increased infrared opacity raises surface temperatures sufficiently to thin sea ice and allow melt ponds and bare ice patches to appear. Once patches of darker wet ice or open water form, they absorb more solar radiation than the surrounding snow, and thick ice further increasing local temperatures. This reduces surface albedo in affected areas and drives additional melting, expanding the darker zones in a positive feedback. As these patches coalesce, large regions of the low-latitude ocean surface become seasonally or permanently ice-free. The resulting reduction in planetary albedo accelerates warming and triggers a rapid transition from a nearly ice-covered state to a climate with much more limited sea ice. Model results and geological inferences from rapidly transgressive postglacial strata both indicate that this transition can occur on timescales that are short compared with the preceding glacial interval on the order of thousands to tens of thousands of years rather than millions. During this deglacial phase, continental ice sheets thin and retreat toward higher elevations and higher latitudes. Large volumes of meltwater flow from ice margins into the ocean, raising global sea level and flooding formerly exposed continental shelves. Where isostatic adjustment lags behind ice loss, relative sea level rise in some basins can be especially rapid. As grounded ice margins retreat across continental shelves, proglacial lakes, fjords, and shallow marine embayments form and expand, capturing sediment and routing meltwater through complex drainage networks. Icebergs carved from collapsing marine-terminating glaciers and ice shelves continue to deliver debris to the ocean, but as grounding lines retreat, the locus of iceberg production shifts landward, and the character of glacial marine deposition changes. The atmosphere above a deglaciating cryogenian Earth is strongly influenced by the very high carbon dioxide concentrations that have accumulated during the glacial interval. As sea ice pulls back and open water areas increase, evaporation from the ocean's surface rises sharply, raising atmospheric water vapor content. Water vapor itself, a greenhouse gas, amplifies the warming driven by carbon dioxide. With a darker surface and a moist atmosphere, the planet enters a super greenhouse state, in which global mean surface temperatures are much higher than before glaciation, and higher than in many other parts of the Proterozoic. Climate model simulations of the aftermath of Marinoan-style snowball states produce global mean temperatures on the order of several tens of degrees Celsius in high carbon dioxide scenarios, with particularly warm conditions in low and middle latitudes. The hydrological cycle under such conditions is vigorous. Strong evaporation in tropical and subtropical regions feeds deep convection and intense precipitation, while enhanced meridional temperature gradients in the atmosphere support energetic storm tracks. Over land, heavy rainfall falls on freshly exposed, largely unvegetated surfaces composed of glacial deposits, bedrock and uplifted rift shoulders. These surfaces are rich in minerals that are easily weathered, especially mafic and ultramafic rocks, from large igneous provinces and rift-related magmatism. Warm temperatures and abundant rainfall produce high rates of chemical weathering, which consume atmospheric carbon dioxide and generate large fluxes of dissolved ions and alkalinity, carried by rivers to the ocean. Mechanical erosion by rivers and mass-wasting processes add substantial clastic sediment loads, filling nearby basins and building new deltas and submarine fans. As ice sheets shrink, glaciostatic rebound raises formerly depressed crust, further reshaping drainage patterns and relative sea levels on regional scales. In the ocean, deglaciation initially produces a strongly stratified water column. Massive inputs of low salinity meltwater from continental ice sheets and from the melting of sea ice form a relatively fresh surface layer that caps deeper, more saline waters. This layer is warmed by the super greenhouse atmosphere and by enhanced absorption of solar radiation once ice retreats. Beneath it, deeper waters retain the temperature and chemical characteristics acquired under the ice, including high salinity, and in many models and geochemical reconstructions, low oxygen concentrations and elevated levels of dissolved, reduced species such as ferrous iron. The strong density contrast between the warm, fresh surface layer and the cold, salty, deep layer impedes vertical mixing, allowing the stratification to persist for significant periods. Over time, wind-driven circulation re-intensifies as sea ice disappears, and overturning currents begin to erode the stratification. Climate model studies suggest that the breakdown of this freshwater cap and the return to a more thoroughly mixed ocean can take on the order of thousands of years, during which the structure of currents and deep-water formation sites adjusts to the new boundary conditions. As mixing proceeds, oxygen from the atmosphere penetrates deeper layers, and reduced chemical species in the ocean interior are oxidized. This reoxygenation process is recorded in changing redox-sensitive trace metal patterns and sulfur isotope signatures in sediments deposited after cryogenian glaciations. The large fluxes of dissolved inorganic carbon and alkalinity delivered to the ocean during and after deglaciation, together with the evolving stratification and mixing drive, high degrees of carbonate supersaturation in surface and shallow subsurface waters in many basins. Under such conditions, rapid precipitation of carbonate minerals occurs on shallow shelves ramps and other topographic highs, as well as in some deeper settings. This precipitation contributes to the formation of cap carbonates that blanket glacial deposits and shallow seafloors. In some models, cap carbonate deposition proceeds in stages. During an initial phase, mixing between alkaline deep waters that accumulated beneath the ice and fresh meltwater leads to widespread carbonate precipitation as waters become oversaturated. In a second phase, intensified continental weathering under the super greenhouse climate continues to supply alkalinity and calcium to coastal and shelf seas, sustaining carbonate formation as meltwater fluxes decline. At later stages, as atmospheric carbon dioxide begins to fall in response to strong weathering uptake, and as the ocean circulation approaches a new quasi-steady state, carbonate precipitation slows and transitions into more typical platform and slope styles seen in early Ediacaran successions. Over the longer term, the combination of high weathering rates, rapid carbonate burial in cap units, and overlying successions and progressive mixing and reoxygenation of the ocean draws atmospheric carbon dioxide down from its deglacial maxima toward lower values, ice retreat, sea level stabilization, and the establishment of new patterns of nutrient delivery and redox structure in the ocean bring the Cryogenian Ice Age interval to a close. At that point, Earth's surface and oceans differ in important ways from their preglacial state, reflecting the combined imprint of prolonged low-latitude glaciations, extreme greenhouse forcing rapid deglaciation, and post-glacial adjustment of the coupled climate and geochemical cycles.